to do the self-checks from lessons 3 and 4, so the second half of the review for the unit test. All right, so let's get started. When you cook food by stir frying, it's important to transfer the thermal energy to the food as quickly as possible. Which of these metals would be the best choice for a pan intended for stir frying vegetables? So remember, this goes back to this concept of thermal conductivity, which is thermal conductivity is how well substances, we say, conduct the energy, and conduct is another way of saying that the energy transfers. Remember? So we have aluminum is like 205, and the lowest one here is, let's say, polystyrene foam, styrofoam, right? So, um, so you can see this example. The example I always used in class, right, was when if you just go right now and you go touch something that's plastic or wood that's been sitting out in the room that you're in, it probably doesn't feel, especially right now since it's winter time, it probably doesn't feel much different than room temperature. But if you go touch metal, anything that's metal, you'll notice that it feels a lot colder to you. And that's not because the metal is actually colder, it's actually just because it has a greater thermal conductivity. So it is better at transferring the energy from your hand to itself because it transfers thermal energy better. And remember, your hands are 98.6 degrees or so. So your hands are going to be warmer than just things sitting around in the room. So if you touch metal, the energy from your hand will go to the metal. If you touch a wooden table, the energy is going to be going from your hand to the wooden table. But you can see how wood is much less conductive than metal. So it transfers the heat away slower, so it doesn't feel like it's as cold. That sensation of cold is energy leaving your hand. So it's kind of a overview of thermal conductivity. And so obviously the best one would be copper. Copper is going to be the best for stir frying vegetables because it has the highest thermal conductivity. Why would a light colored roof be preferable to a dark roof in a warm, sunny area? And this goes back to the idea that light colors will absorb energy in the form of light energy or radiation slower than dark colors. So you wouldn't want a dark roof in a warm, sunny area because it will heat up more than a light colored one will. You can do this yourself if you wear like a white t-shirt or you wear a black t-shirt on a hot sunny day. You will feel hotter if you are wearing like a darker colored shirt than a light colored shirt. So the dark colored roof will not cool the house as quickly at nighttime. That could be, no, that's not totally true because saying it's cooling off the house itself. The dark colored roof absorbs more energy during the day and becomes hotter. Yep. The light colored roof absorbs more energy. That's not true. The light colored roof cools the house faster. So the problem with these, this one kind of almost sounds right, but the problem with these is these questions are both saying that the roof cools the house. The roof cools the house. The roofs do not cool down houses. So neither of those can be right. If you place a hot piece of metal in a container of water, thermal energy flows from the metal to the water. What happens after the metal and the water reach the same temperature? So this is assuming that the hot piece of, see, this is a hot piece of metal and it's placed in water. So the water would be colder. If the thermal energy is flowing from the metal to the water, that means that the metal was hotter than the water. So after they're both the same temperature, the flow of thermal energy stops and the temperature remains constant. The flow of thermal energy continues and causes both to become warmer. The flow of thermal energy reverses. Both things become warmer. The flow of thermal energy reverses and the water becomes colder. So imagine this yourself. You have something that's hot and you put it in a glass of water and it's not plugged into anything. It's not going to stay hot, right? Like you have some hot coins that you put them outside on a sunny day and you put them in a glass of water. What's going to happen? eventually the flow of thermal energy stops and the temperature will remain constant. So the flow of energy can't continue because eventually the the hot metal won't be hot anymore, right? So it can't just magically make the water warmer forever. And the flow of thermal energy won't just magically reverse and start making both things warmer, and it won't reverse and make both things colder. The water they will become colder eventually, but they're not losing uh, their thermal energy because the energy reverses and starts going back into the metal. It's just that both the metal and the water will start losing the energy to the air and the environment around it. Okay, 4. There are 2 streams of liquid flowing through the heat exchanger. Here's the picture. As these streams pass opposite sides of the tubes, thermal energy transfers from. So, where is this going? So, this diagram shows a heat exchanger used in chemical processing plant. Thermal energy is transferred between the liquids flowing through the tubes in the exchanger. Okay, so you can see how here you want to look at the inputs and the outputs. So, what are we doing? So, liquid A, right? We have hot water coming in, and it goes through some pipes, and it looks like, you see how this is dark red and light red? So it's cooling off, and then it leaves. And in the liquid B, cold water is coming in, it's circulating with this in these pipes around the hot water, and then it leaves. It's a little lighter blue. It's warmed up a little bit. See, actually, you can see the temperatures. It's warmed up. It went from 20 degrees to 35 degrees. The hot water at 80 cooled down to 60. So what's happening? The thermal energy transfers from the hot. It's always hot to cold, right? Which is the hot liquid? Liquid A is the hot liquid. So it's transferring from liquid A to liquid B. It's a fancy diagram, but at the end of the day, remember, it just heat goes from hot things to cold things. How does the flow of thermal energy in a solid object change when it's taken from a warm building out into the cold? So the hot solid object would lose its thermal energy to the air slowly from convection, and it would lose energy to anything colder that it's touching through conduction. So anything that it's basically a solid object, and you take it out from a warm building, you put it outside. What's happening? How's it losing energy? Well, if it's touching anything, it's going to lose it through conduction. That's, remember, things are touching. But it's also going to heat up the air around it that it's touching, and that air will kind of move out of the way, and that's convection. So it's losing its energy. What states of water do you directly observe in this photo? All of it. Why all of it? Well, what a nice picture. It's a little blurry though. This is a stream. Maybe you don't spend much time outdoors. This is a stream. This is definitely a stream. So this is liquid, right? Even if the top of this is frozen, because you're like, it's icy, it's frozen. Well, it's not all frozen. Streams don't completely freeze solid, which you might not know. But if you have ever actually gone out to the wilderness in the winter, the streams won't fully freeze over. They're moving, which will give them enough kinetic energy usually to stay liquid under the surface. So there's liquid down here. There is gas in the air, right? There's always, in the air, there's always gas, water in gas form. And then it's also, obviously, the easy one is solid. It's frozen. Like, it's snowing, that's frozen. And there's snow on the ground, that is solid water. So 7, as snow forms in the atmosphere, the water molecules lose kinetic energy. So they're losing energy as the snow is forming, right? They are coming together and they are getting colder, which means that if you think of it on a subatomic level, right, hot things are moving quickly and colder things are moving slowly. So they're losing kinetic energy. How will the environment shown in the photo change when summer arrives? Well, let's see. The snow will melt, for sure. The water will evaporate from the stream. That would be happening. Now, maybe not all of it, but the water is, it doesn't say all the water, it's just saying the water will evaporate from the stream. So I'm saying that this is true because water would definitely be evaporating from the stream. Transpiration could occur. That is true. Remember, transpiration is the word that we use for evaporation from plants. So the leaves, water from the grass and the needles in the tree will be evaporating. We call that transpiration. And snow will definitely not continue to form and fall much paths. Which of the following steps in the water cycle can you infer are taking place in this scene at the moment the photo was taken? Okay, evaporation is taking place all the time, even very slowly, right? Sublimation is also happening. Sublimation, right, is the how the molecules on the very outside of solid surfaces are slowly heating up from outside energy and evaporating. So they go directly from solids to a gas. And that does happen, and you can see that in ice in your freezer. We've talked about how the ice seems to shrink. It's not really shrinking, it's just going straight, it's sublimating. It's going straight from a solid to a gas. Condensation, I do not see happening here. Transpiration would be happening. So trees are still losing moisture to the air through transpiration, even when it's cold. It just happens much less. Condensation would be when there is, I guess I could see there's condensation because it seems I can't really tell if this is cloudy or foggy in the back or if it's just because it's snowing. But let's say it's foggy. Let's say you think that it's foggy. If it's foggy, then there's also condensation, which means that the water molecules in the air, it's cold enough that they are condensing into like a fog or a cloud situation. And so they could all be happening. Using numbers 1 through 4, order the following events in the sequence that most logically describes the movement of water from the ocean to the bottom of a well in the village on an island. From the ocean to the bottom of a well. So it's starting in the ocean. So a well, this is a little bit tricky because you might be thinking that the water is somehow going directly into the well, right? But remember, a well, the concept of wells, if you don't actually know how wells work, is a well is you are digging really deep down into the ground until you reach water that has soaked into the ground that's already there. It's not necessarily collecting water from the sky. Wells don't, they can collect rain, but a lot, I'm sure if you've seen those classic Disney movies, right, like Snow White, there's like the little housey roof thing over the well, so it's not collecting the rain. So what's most likely happening is you have the ocean water and it is evaporating first into the sky, and then it is going to condense into clouds, and then it's going to precipitate or rain down to the ground, and then finally it will infiltrate, which is the water is going to soak into the ground and then the water is in the ground where it would be for a well that's been dug. And the end. Water in the clouds in this scene eventually move from the atmosphere. Oh, so see this as water in the clouds in this scene. So there are clouds in that scene. So we definitely do have condensation. Move from the atmosphere to the land by, let's see, from the atmosphere to the land by, okay, so they're talking about water in the clouds. Where's the water from the clouds going? So the water is going to go from the clouds to the land by precipitation, right? That's how water would go from a cloud to land. Next, something carries that water to the sea. That would be, so transpiration is right, evaporating from plants. Melting would be the liquid snow melting. Runoff is when water is moving, like running down streams. So runoff would be carried to the sea. Streams, rivers, those are examples of runoff. And wind, gravity drives both of these water movements. So all of this is driven by gravity. And use a sequence of at least 4 events to describe some ways that water moves into, through, and then out of the atmosphere. Okay, so you take a drink that's old and gross. So you spit it out. It soaks into the ground. That is infiltration. Okay. Then eventually it will evaporate. So then it will eventually evaporate. That's the next one. Finally, it condenses into clouds and eventually precipitates down. So there's 4 events. And, oh no, I can't get to this because my screen. Zoom out. Here, I'll just delete this for now. The last question is explain the roles of sunlight and gravity in the water cycle. So sunlight, I'm not gonna type this because it's I'm sure you don't like watching me type and trying to talk at the same time. So sunlight provides the energy that sunlights provide, right? That drives things like any of the processes where things need more energy. So it's driving the evaporation from the bodies of water. It's driving transpiration from plants. It's also driving the sublimation, which is the solids getting energy so that they can evaporate directly to a gas. That is all driven by energy from the sun. And then gravity is the reverse. Gravity is causing the condensation, right? Because gravity is causing all of the individual water molecules, right, have their own mass, and gravity will draw them together as they lose kinetic energy. And so the condensation, the precipitation falling down, and also the runoff, right? The water going from like higher up in the mountains running down towards the oceans, that's all driven by gravity. So there you go.